The building you are looking at is nearly 1,900 years old. Its dome is 43.3 meters across, 142 feet. It is still the largest unreinforced concrete dome on Earth. No steel reinforcement, no modern support systems. Just concrete from the 2nd century, holding itself up across a span that architects and engineers, with computers and advanced materials, science have not surpassed in the 2,000 years since it was built. It is not a ruin. It is a working building. There is a church inside it. On an ordinary Tuesday afternoon, you can walk in, buy a ticket, and stand beneath that dome and look up through the oculus at the open sky, just as people have been doing since the Emperor Hadrian completed it around 126 CE. The concrete in that dome is not crumbling. It is not visibly deteriorating. It has survived dozens of earthquakes that have destroyed newer buildings around it. It has been rained on, frozen, heated, and subjected to nearly 2 millennia of Roman pollution, and it is structurally sound. Meanwhile, across the world, concrete highway bridges built in the 1970s are being demolished and replaced because they have reached the end of their designed lifespan. The American Society of Civil Engineers estimates the United States alone needs to spend approximately $4.5 trillion to fix its deteriorating modern infrastructure. Roman concrete lasts 2,000 years. Portland cement, the concrete that replaced it, the concrete we use for almost everything today, is designed to last between 50 and 100. We lost the formula for something vastly superior. We used the inferior replacement for 2,000 years. And we only just figured out why Roman concrete worked. In January 2023, a team led by Admir Masic at MIT published a paper in Science Advances that reversed a century of scholarly assumption about Roman concrete. They found a self-healing mechanism that no one had previously understood, a chemical process built into the material itself that allowed it to repair its own cracks as they formed. In 2025, a separate team published findings from an excavation at Pompeii that confirmed the mechanism from the archaeological record. They had found a construction site frozen in the middle of work by the eruption of Vesuvius in 79 CE, dry ingredients sitting in piles beside walls under construction, a snapshot of Roman building practice preserved for 2,000 years by volcanic ash. This is the story of what Roman concrete was, how we lost it, why Portland cement is a worse material doing the same job less well at enormous environmental cost, and what those two papers mean for the future of one of the most important industries on Earth. Subscribe to Archives Untold. This video is not just about Roman engineering genius. It is about what happens when a civilization loses something it doesn't know it's losing, and what it costs the rest of history to get it back. Because the story of Roman concrete is also the story of modern concrete. And modern concrete is responsible for 8% of global CO2 emissions every year. So this matters more than you might think. Roman concrete is not what you picture when you think of modern concrete. Modern concrete, Portland cement concrete, is a mixture of cement powder, water, sand, and gravel. The cement is made by heating limestone and clay to temperatures above 1,427 degrees Celsius, which drives off carbon dioxide and creates a highly reactive powder. When you add water, the powder chemically reacts and hardens within hours into a rigid, stone-like mass. It is fast, it is strong in compression, and it begins deteriorating from the day it is made. Roman concrete, opus caementitium, was built on a completely different chemistry. The foundation of the formula was pozzolana, a fine volcanic ash found in abundance around the Bay of Naples, particularly near the town of Pozzuoli. The word pozzolana comes directly from that place name. The ash is rich in reactive silica and alumina, the compounds that give it its remarkable properties. The Romans understood empirically, if not chemically, that this ash was special. The architect Vitruvius, writing around 25 BCE, described it in his 10 books on architecture. There is a kind of powder which from natural causes produces astonishing results. It is found in the neighborhood of Baiae and in the country belonging to the towns round about Mount Vesuvius. This substance, when mixed with lime and rubble, not only lends strength to buildings of other kinds, but even when piers are built of it in the sea, they set hard under water. Marcus Vitruvius Pollio, De Architectura, circa 25 BCE, sets hard under water. That observation, made 2,000 years ago by a Roman architect, is the key to everything. Roman harbour concrete did not merely resist the sea. It hardened in contact with seawater. It became stronger over time as seawater percolated through it and triggered new chemical reactions. The ruins of Roman harbour structures at Caesarea Maritima in Israel, built between 22 and 15 BCE, are still largely intact. 21 centuries of the Mediterranean Sea. And they are still there. The mixture itself was layered rather than poured. You packed a wooden framework, or simply the sea itself, when building harbours, with coarse aggregate, broken rock, rubble, brick fragments, pieces of tuff. Then you poured or troweled the mortar, the mixture of lime and volcanic ash, over and between the aggregate. The result was not uniform. It was a composite, like a geological formation, with the mortar binding the aggregate into a single, coherent mass. For the Pantheon's dome, the Romans did something even more sophisticated. They varied the aggregate by density as they built upward. At the foundation, dense travertine limestone, which has a density of approximately 2,200 kilograms per cubic meter. Moving up through the walls, lighter tuff. At the crown of the dome, pumice, the lightest volcanic rock full of trapped air pockets with a density around 1,350 kilograms per cubic meter. The dome was not uniform concrete. It was graded, layer by layer, growing lighter as it rose, mimicking, in a sense, how geological formations layer themselves, putting the weight where the structure needed it and removing weight where the structure didn't. Modern engineers, using computer modeling and materials science that would have been incomprehensible to any Roman architect, have studied the Pantheon's dome extensively. The conclusion that keeps emerging from these studies is not flattering to modernity. An unreinforced concrete dome of that diameter, built today using Portland cement, could not be expected to last a century. The Romans built one that has lasted 19. For 400 years, from roughly 150 BCE to 250 CE, Roman concrete was the dominant building material of the Mediterranean world. It built the aqueducts that supplied Rome's million residents with water. It built the harbours that handled the trade of an empire. It built the public baths, the civic basilicas, the apartment buildings, the roads. And it did all of this without steel reinforcement, without power equipment, and without a single chemistry textbook. They built it by doing, by observation, by inherited knowledge, by the accumulated experience of generations of Roman engineers who knew what worked. They did not know why it worked. The why would take until 2023 to fully answer. Let us be specific about the marine concrete, because the marine concrete is where the most remarkable chemistry happens. When the Romans built harbour structures, they sometimes poured concrete directly into wooden forms submerged in seawater. This is counterintuitive to anyone familiar with modern construction. Modern Portland cement concrete deteriorates rapidly in seawater. The salt crystallizes inside the pores, creating pressure that fractures the material from within. Marine structures built with Portland cement typically last less than 50 years before requiring significant repair. Some submerged concrete piles have failed within a decade. Roman harbour concrete did the opposite. Researchers studying cores, drilled from the ancient harbour at Caesarea Maritima and from harbour structures along the Italian coast, found something that took years to fully explain. The concrete was not just intact. In many samples, it appeared to be in better condition than when first built. As seawater had percolated through the material over the centuries, it had not eroded the concrete. It had triggered new crystal growth inside it. The specific crystal is called aluminous tobermarite, a mineral with long, plate-like crystals that have an unusual property. They are flexible. They bend rather than break under stress. As seawater reacted with philipsite, a mineral naturally present in the volcanic ash, tobermarite crystals grew throughout the concrete matrix. The structure became, over time, reinforced from within by a mineral that Roman engineers had no knowledge of and no way to plan for. The sea was not their enemy. It was their collaborator. Marie Jackson at the University of Utah, who led much of the research on the marine concrete, described the result as a candidate for the most durable building material in human history. The most durable building material in human history, made with volcanic ash, lime, and seawater, by people who thought the ash had special powers because it came from near a volcano. They were right. It did have special powers. They just didn't know what the powers were. There is a harbour breakwater at Caesarea Maritima that was built between 22 and 15 BCE. Herod the Great commissioned it, the same Herod who built the Second Temple in Jerusalem, the same Herod who ordered the killing described in the Gospel of Matthew. The breakwater he built on the Mediterranean coast is still there. Pieces of it are still structurally sound. 2,040 years of the sea. And the Roman concrete is still doing its job. Portland cement concrete in a marine environment. 50 years, maybe less. 2,000 years versus 50. That ratio, that specific scandalous gap, is why the MIT team's 2023 paper mattered to people far beyond the materials science community. Because understanding why Roman concrete works is not merely a historical curiosity, it is potentially one of the most important practical discoveries of the 21st century. Roman concrete did not disappear because anyone forgot the recipe. It disappeared because the recipe required something that could no longer be supplied. Pozzolana, the volcanic ash that made the concrete work, came primarily from the Bay of Naples, specifically from deposits near Pozzuoli and from other volcanic regions of central Italy. To build harbour structures anywhere in the empire, the Romans shipped pozzolana thousands of miles. 20,000 tons of it crossed the Mediterranean to build the harbour at Caesarea Maritima alone. This was not a local material. It was a specifically Italian volcanic product distributed across an empire by a functioning trade network of extraordinary complexity. When the Western Roman Empire collapsed in the 5th century CE, that trade network collapsed with it. Not all at once, not on the day in 476 CE when the last Western emperor was deposed, but gradually, over the course of a century of instability, invasion, and economic contraction. The shipping routes that had carried pozzolana to Carthage and Caesarea and Londinium stopped functioning. The institutional knowledge that specified which ash from which deposit, mixed with which lime, in which proportions, began to disperse. No single catastrophe erased it. It simply stopped being taught, stopped being needed, stopped being used. By the 7th century, large-scale concrete construction had essentially ceased in Western Europe. Builders returned to what they could source locally: stone, brick, timber. These are not inferior materials. The medieval cathedral builders achieved extraordinary things with cut stone, but they are different materials. You cannot pour stone into a harbour. You cannot build a dome in stone that spans 43 meters without steel reinforcement. The knowledge that concrete could be made from volcanic ash and lime was not entirely forgotten. Some remnant of the understanding survived in medieval manuscripts, in fragments of Vitruvius copied by monks who did not fully understand what they were reading. But the specific know-how, which ash, from where, in what proportions, mixed in what sequence, that was gone. Then, in 1824, a bricklayer from Leeds named Joseph Aspdin patented a new kind of cement. He made it from limestone and clay, mixed together and baked in specific proportions. He called it Portland cement because he thought the resulting stone resembled Portland limestone, the popular building material used for St. Paul's Cathedral. Portland cement set fast, much faster than Roman concrete, which could take decades to reach full strength. It was strong in compression, it was reproducible. The same formula, the same proportions, the same kiln temperature, the same result every time. It could be made anywhere, from ingredients available everywhere. It did not require the volcanic deposits of the Bay of Naples. Portland cement was a genuinely useful invention. It enabled the construction boom of the 19th century. The railway bridges, the canal locks, the factory floors, the Victorian infrastructure that made industrial civilization possible. It was not a bad material. It was simply an inferior one for certain purposes, by certain measures, in ways that Aspdin and the engineers of the 19th century had no way to know. They didn't know about tobermarite crystals. They didn't know about self-healing lime clasts. They didn't know that the volcanic ash from Pozzuoli triggered chemical reactions that would strengthen concrete over millennia rather than weakening it. They built with what they had, and what they had was better than nothing, and better by many measures than the stone and timber that preceded it. But it was not as good as what the Romans had used, and we didn't know that. For 1,400 years after Roman concrete went out of use, we did not know what we had lost. For years, archaeologists and materials scientists studying Roman concrete had noticed something puzzling. Embedded throughout the ancient mortar, in samples taken from walls, from harbour structures, from the Pantheon itself, were small white chunks, millimetre scale, bright white, visibly distinct from the surrounding grey-brown mortar matrix. Every sample had them. They appeared everywhere that Roman concrete appeared. The conventional explanation was embarrassing. Scholars assumed these white chunks, called lime clasts, were manufacturing errors. The Romans, it was thought, had failed to fully mix their lime into the mortar. The white chunks were pockets of incompletely hydrated calcium oxide, basically lumps of undissolved ingredient, imperfections, evidence that Roman concrete, for all its remarkable durability, was not always well mixed. Admir Masic was not satisfied with this explanation. Masic is a materials scientist at MIT. He had been studying Roman concrete for years, and something about the lime-clast explanation bothered him. Roman concrete was, by every measurable outcome, an extraordinarily successful building material. The structures it had produced had lasted 2,000 years under conditions that destroyed modern concrete in decades. If the lime clasts were manufacturing errors, they were errors that correlated perfectly with exceptional durability. That seemed wrong. In 2023, Masic's team published their findings in Science Advances. The lime clasts were not errors, they were the whole point. The team discovered that the Romans had been using a technique called hot mixing. Instead of the conventional process, slaking the quicklime by combining it with water first, letting it cool, then adding the volcanic ash, the Romans mixed the quicklime directly with the dry volcanic ash without adding water first. When water was finally added to this dry mixture, the reaction that occurred was violent and exothermic. The quicklime reacted immediately with the ash in an intense chemical process that generated enormous heat. This was dangerous. The mix temperature during hot mixing could reach hundreds of degrees. The workers handling it needed to work quickly and carefully. It required skill and knowledge passed down through generations of practice. But the danger produced a miracle. During the hot mixing process, the rapid reaction left some of the calcium oxide incompletely integrated into the mortar matrix. These unreacted pockets of calcium oxide, the white chunks that archaeologists had been calling manufacturing errors, remained embedded in the hardened concrete as small reservoirs of reactive calcium. When water seeps into a crack in Roman concrete, rain, groundwater, seawater, it dissolves calcium from the nearest lime clast. The dissolved calcium recrystallises as calcium carbonate, filling the crack from within. The crack seals itself. The material heals. The lime clasts are not imperfections. They are a distributed self-repair system, embedded throughout the material, waiting for damage to occur so they can fix it. A material that responds to injury. A concrete with an immune system. Masic's team went further. They created modern concrete using the hot mixing technique, then mechanically fractured it. They allowed water to flow through the cracked samples. Within 30 days, the cracks had completely sealed. Water flow through the samples ceased. The repaired sections showed new calcium carbonate crystal growth filling the fractures. 2,000 years of Roman concrete's exceptional durability explained in a single mechanism. The lime clasts were not the result of carelessness. They were the result of a specific, deliberate, dangerous mixing process that left chemical reservoirs throughout the material. Every time the concrete cracked, the crack triggered its own repair. The Romans did not know this. They could not have known this. They had no chemistry, no microscopy, no crystallography. They knew that mixing quicklime with dry ash before adding water made very hot concrete that set well and lasted. They knew this from generations of practice. The chemical reason behind it was invisible to them. They had stumbled into one of the most sophisticated building material formulations in human history, and they had no idea how deep the sophistication went. If the 2023 MIT paper told us how Roman concrete worked, the 2025 paper told us that we were right. In Pompeii's Regio 9, the northwestern residential quarter of the city, archaeologists had been working through a neighborhood that was undergoing repair and reconstruction when Vesuvius erupted on the 24th of August, 79 CE. Earthquakes had damaged many of the buildings in the years before the eruption, and the neighborhood was an active construction zone. Workers were in the middle of rebuilding walls. Some walls were complete, some were half-built. And beside the half-built walls, still in the place where they had been set down when the sky went dark and the ash began to fall, were the raw materials, separate piles of dry quicklime and dry volcanic ash, not yet combined, waiting to be mixed. The eruption that killed 2,000 people and buried an entire city also preserved, at the cost of everything else, the most perfect possible record of Roman construction practice. The research team, led by Masic and colleagues from multiple institutions, collected samples from the completed walls, from the walls in mid-construction, and from the raw material piles themselves. They subjected everything to microstructural and chemical analysis. The results confirmed what the 2023 paper had proposed. Quicklime and dry volcanic ash were transported to the site separately and mixed dry before water was added. The hot mixing technique, proposed from chemical analysis alone in 2023, was now confirmed directly from the archaeological record. Around the volcanic aggregate particles embedded in the mortar, the team found what they called reaction rims, zones where the calcium from dissolving lime clasts had diffused outward into the surrounding volcanic material, triggering new chemistry at the interface. The concrete was not a static, inert material. It was a chemically active system. 2,000 years after the workers left their unmixed piles of quicklime and ash and ran from the volcano, the chemistry those materials created was still, in principle, operating. Masic's comment to Chemistry World about the 2023 paper: "This is not an archaeology paper. It is a badass chemistry paper," applies equally well to the 2025 confirmation. These are not sentimental discoveries about the cleverness of ancient Romans. They are discoveries about a building material of extraordinary practical importance, made at a moment when the building material that replaced it is becoming one of the more pressing environmental problems the world faces. The Pompeii construction site is sometimes described as a snapshot. That is exactly right. It is a snapshot of workers doing something that was to them unremarkable, mixing quicklime and volcanic ash in the way they had always mixed it, in the way their teachers had shown them, in the way their teachers' teachers had shown them. They were not doing something extraordinary. They were doing their jobs, and their ordinary working process, preserved by extraordinary disaster, turned out to contain the answer to one of the most important materials science questions of our time. Here is the question the series always asks at the end, in the form specific to this story. Antikythera asked, "What else from the ancient world are we missing?" Damascus Steel asked, "What happens when knowledge that lives in people dies with them?" Greek Fire asked, "What happens when the institution guarding a secret is destroyed?" Hero of Alexandria asked, "What happens when you have the principle but not the conditions to use it?" Roman concrete asks something different from all of them. It asks, "What happens when you find it again?" Because that is what has actually happened, not a discovery of something that existed and is now gone, a mystery unresolved, a haunting absence, a discovery of something that existed, was lost, was used in an inferior form for 2,000 years, and has now, in the first quarter of the 21st century, been recovered well enough to replicate. Masic's team at MIT is working to commercialize a modern version of Roman-inspired concrete. The University of California, Berkeley has already recreated it using volcanic rock from California's coast ranges. The U.S. Department of Energy's ARPAE, the Advanced Research Projects Agency Energy, has funded projects specifically aimed at developing Roman-inspired concrete formulations for commercial use. The environmental stakes are not small. Portland cement production currently accounts for approximately 8% of global carbon dioxide emissions. That is a larger share than aviation, larger than shipping, comparable to the entire agricultural sector of many countries. Modern concrete is one of the most widely used materials in human history. Only water and air are consumed in greater volumes, and making it is extraordinarily carbon-intensive. Firing limestone at over 1,427 degrees Celsius at industrial scale across the entire global construction industry releases roughly 0.95 kilograms of CO2 for every kilogram of cement produced. Roman-inspired concrete could change this, not because it produces zero emissions, it does not, but because it lasts so much longer. A structure built with Roman-inspired concrete and designed to last centuries rather than decades requires less cement, less aggregate, less energy, less raw material over its lifetime. A 2025 comparative study confirmed that despite higher initial energy requirements for the hot mixing process, Roman-style concrete's extended lifespan makes it more sustainable over time. The embodied carbon of a structure, calculated over its full service life, is far lower when the structure lasts 2,000 years than when it lasts 50. There are challenges. Pozzolana, the specific volcanic ash from the Bay of Naples, is not available at the scale needed for global cement production. Researchers are working on analogues: coal fly ash, volcanic deposits from other regions, engineered materials that can replicate the key chemical properties. The hot mixing process requires more careful handling than standard Portland cement production. The scale-up, from laboratory to construction site to global industry, involves engineering, logistics, and commercial problems that the 2023 and 2025 papers have not solved. But the principle is known. The mechanism is understood. The confirmation from Pompeii gives engineers and materials scientists something they have not had before: a direct archaeological blueprint of the process, not just a reverse-engineered hypothesis from chemical analysis of finished structures. They know what to mix, in what sequence, at what stage. The recipe, the actual recipe, the one the workers in Pompeii's Regio 9 used before they dropped their tools and ran, is recoverable. This is what makes Roman concrete unique in this series. We are not standing at the end of the story, looking back at something that was lost and marveling at the loss. We are standing at the beginning of a recovery. The Pantheon Dome has stood for 1,900 years. The harbour at Caesarea Maritima has been resisting the Mediterranean for 2,000. We now understand why. We now know how to make it again. We are, if we choose to use this knowledge, at the beginning of a new era of concrete, one that learns from the Romans not just architecturally, but chemically. One that does not simply admire the Pantheon from a distance, but asks seriously and with engineering rigor what it would take to build its equivalent today. There is an oculus in the Pantheon's dome, the circular opening at the very top, 9 meters across, open to the sky. No glass, no cover. When it rains, the rain falls through the oculus onto the ancient marble floor. The floor has a slight convex curve and drainage holes, placed there by Roman engineers who knew the rain would come and designed accordingly. The building accommodates the weather. It does not resist it. It works with it. That is, it turns out, also the key to why the concrete works. It does not resist the water. It works with it. When water enters, chemistry begins. Cracks seal, crystals grow. The material repairs itself. The Roman engineers who built this did not know the chemistry. They knew the practice. They knew it worked. And after 2,000 years and 2 landmark papers from MIT and Pompeii, we finally know why. Thank you for watching. Subscribe to Archives Untold. Every week we find the stories that history buried, and sometimes the stories that history buried are the ones we most urgently need to dig up. Leave a comment. Do you think Roman-inspired concrete can be scaled up to replace Portland cement? Because the answer to that question might matter more than most of us realize.